In this video, we are going to be talking about liquefaction of gases and the critical phenomenon. So first of all, when you have a gas, when we cool it down, or rather when we decrease the temperature or when we increase the pressure, this is going to lead to the liquefaction, or it's going to get liquefied. So as we know, gases like carbon dioxide, sulfur dioxide, ammonia, H2S, etc. were liquefied by two things, by cooling or by compression. Cooling involves the decreasing of temperature, whereas compression involves the increase of pressure. So this is all based on, so first of all, according to the kinetic molecular theory of gas, the attractive forces between these molecules of a gas are going to be negligible. So when you have the high temperature, what will happen is the molecules of the gas will start moving around more vigorously or more fast, and it will not basically be able to come in contact with each other and liquefy. But as we decrease the temperature, the kinetic energy is going to decrease. This in turn will slow down the gas molecules, and there'll be a particularly low temperature where the molecules are close enough for the attractive forces to actually be strong enough for basically condensation or liquefaction to take place. And at that point in time, the molecules cannot resist the force of attraction. Not only that, when you have a increase in pressure, it will start pushing these molecules of gases closer together, and this in turn will lead to the gas liquefying. So in conclusion, a gas can be liquefied by decreasing temperature or by increasing pressure or by applying both conditions together. So the conditions for liquefaction were studied by Thomas Andrews in the year 1869. So what he gave us the pressure volume isotherm of carbon dioxide. So he plotted a graph between pressure and volume at various temperatures and compared these isotherms which were observed. Now, carbon dioxide need not necessarily behave like an ideal gas under all conditions of temperatures. So, he noticed that when the temperature was low, carbon dioxide tended to behave like an ideal gas. Sorry, does not behave like an ideal gas when the temperature was low. So, at 50 degrees Celsius, you notice that it's almost similar. The isotherm for carbon dioxide is similar to that of an ideal gas. So we will be studying about this graph in detail, okay, and that's going to help you understand. First of all, before we move forward, in this area, carbon dioxide is going to be a gas. In this area, it's going to be a liquid. Okay, the shaded portion I will tell in a little bit as to what it shows. Now, at 30.98 Celsius, so that's this blue color line. Okay, now um, notice, first of all, it goes upwards and then it reaches this particular point and then it's increasing again, right? Now, at 30.98 degrees Celsius, the carbon dioxide is going to be a gas till this particular pressure, that is 73 bar. Or I think it's in atmosphere, if I'm not wrong. Sorry, 73 atmospheric pressure. Now, here, after this pressure, the carbon dioxide is getting converted from a gas to a liquid. So, this is the highest pressure, sorry, temperature at which the carbon dioxide, this 30.98, is the highest temperature at which you're going to have liquid carbon dioxide. Above this, it will always be a gas, no matter how high the pressure is going to be. Even at like this height, if you try and convert carbon dioxide to which is at a 50 degrees Celsius, let's assume it's 50 degrees Celsius, when we are increasing the pressure, no matter how high the pressure is, the carbon dioxide will stay as a gas and it will not get converted to a liquid. So this particular condition of 30.98 is the highest temperature at which carbon dioxide can get converted from a gas to a liquid. And this is called as the critical temperature. Now, when we increase the pressure, what is happening is you can see a curve upwards. Okay. Now, even for a small amount of compressibility that is observed, it leads to a steep increase. This means that carbon dioxide, liquid carbon dioxide, is not very compressible in nature. Okay, now, so that's about it. So 30.98 degrees Celsius, you have first of all till 73 atmospheric pressure, carbon dioxide is a gas. And after that, it gets converted to a liquid. And liquid carbon dioxide, and this particular temperature is 30.98, is the highest temperature at which liquid carbon dioxide appears. Above this temperature, if we, no matter how high the pressure is going to be, we cannot get a liquid carbon dioxide. Okay, now when the pressure is increasing also, you notice there is a slight decrease in there is a decrease in volume, but a steep increase in pressure. This is because even if like some amount of liquid carbon dioxide is compressed, it is leading to a huge increase in pressure, and this in turn shows that carbon dioxide is not that compressible in nature. So we studied at 30.98 degrees Celsius. Next, we are going to be talking about below 30.98. Now, in here, you will notice, okay, so first of all, this graph, this blue line is for 30.98 degrees Celsius. The ones below this blue line, these two lines, especially the one in pink and the one in light blue, both of these are below 30.98. Okay, they're below 30.98, and you have one at 20.5. Okay, and another one at 13.1 degree Celsius. Now, notice, first of all, let's just observe what we see on this graph. Okay, first you see that there's a line, there's a straight line, okay, where you have an increase in pressure with decrease in volume. Okay, volume is going from V1 to this particular value. So there is a decrease in volume and the pressure is going to be P2. And then you notice that there's a constant here. So here there's a constant in terms of pressure, but not volume. Volume is decreasing from B to C. Okay, and then there is a sudden increase in the pressure. The exact same thing is observed, but I guess the only difference between these two is the length of this line that we see. Okay, so what does all of this mean? Okay, first, let's look at point A. Point A is for a particular amount of, or rather, carbon dioxide is a gas at point A. Okay, and when the pressure is increasing from A to B, so pressure, let's say, was somewhere here, it has increased from here to here. So there is an increase in pressure from this particular value, let's say PA to PB. That's a very bad handwriting, I know. So there is an increase in pressure from PA to PB, and so there is a decrease in the volume. Okay, and that's where we stop at point B. And point B is when the process of liquefaction starts taking place. Now, from point B to point C, it's a straight line, which in turn means this particular area actually is comprised of two states. It's going to consist of both gas as well as a liquid. So carbon dioxide gas is going to get converted to the liquid, and that's why it shows a decrease in the volume. Okay, so the volume is changing from this volume to V2 over here. Right, so there is a decrease in volume from point B to point C. Now, there is no change in pressure, okay, but if you notice, what happens is when the pressure is going to be applied, right, and that is in turn going to facilitate the conversion of the gas to a liquid up till point C. Point C shows that the condensation process is complete and you have a liquid carbon dioxide at point C. Now, from point C to, let's say, point D, The volume change is only this much, but there is a huge change in pressure. It's going from P2 to P3. There's a huge change in pressure, and this in turn shows that even a small amount of compressing of that liquid is leading to a huge increase in pressure, right? And this shows that again, a lot of pressure is required to compress the liquid carbon dioxide. The next one is below 30.98. You notice this particular line. As I told you, if you notice, this is actually longer than this line. The CB line is longer than D, G, H. Okay, let's assume this is I and J. I'm assuming those are not. So this particular line, IJ, is actually longer than C and B. So this is because it at a lower temperature, okay, you have this length, this distance, this particular area of the, or rather this length is longer. That was what is observed. Okay, so below 30.98, first of all, we are taking the example of 21.5. At point A, we have a particular volume of carbon dioxide. When the pressure is increasing, it leads to the conversion of the volume from this particular value to this one, and that's where we get to point B. Point B is when the process of liquefaction starts. So in this area, you don't have one, but you have two states, that is a gas as well as a liquid. So pressure will be applied. Okay, that will in turn help the conversion of a gas to a liquid, and that's why you have a constant but line of pressure, but you have a decrease in terms of the volume, and then you have a steep increase that shows that a high amount of pressure is required to compress a liquid carbon dioxide. And C also shows that the process of condensation is complete. Okay, and below this particular 30.98, you will have the same graph which is observed. So it will come to here, it will show flat and go up. So at various conditions of temperature, you will have the exact same thing that is observed, the same shape of the graph that is observed. Okay, so let's continue. So here, this particular point. Now, before we go into that, first of all, this particular point, which is like this one, this represents a carbon dioxide in the gaseous phase. D is going to represent carbon dioxide in a liquid state, whereas this area, this all colored area, represents carbon dioxide in the form of a vapor as well as a liquid as well as a gas. And this is in an equilibrium. Okay, now this okay. Now what happened was, it was concluded by Andrews that gases under all compression undergo compression at constant temperature. They show behavior similar to that of carbon dioxide. So he noticed that many gases, no matter like the different types of gases, he saw a similar pattern in terms of their behavior. Now, if you notice over here, this particular area, what was observed was there is this flat portion at the top. Okay, and this at this portion, this point X, it's at the 30.98 isotherm. Okay, and there is no about this isotherm. If you notice for this green line, okay, this green line is at 31.1 degrees Celsius. There is no straight line which is observed. This portion where it's like that, and then this, and then that, right? So this straight portion is not observed for a gas at a higher temperature. Okay, that's what was noticed. So what it was, I mean, sorry. So what was decided, or rather what was observed, was that beyond this 30.98 degrees Celsius, no matter how high the pressure was, the gas refused to get converted to a liquid. Okay, and that's why this particular temperature is called as the critical temperature. And when gases are present below their critical temperature, they are called as vapors. So the temperature above which, no matter how much pressure is put in, no matter how much pressure is added, even if it is going to be like very high, the gas will not get converted to a liquid. Okay, and that temperature is called as a critical temperature. For carbon dioxide, the critical temperature is going to be 30.98 degrees Celsius. Next, the next one is the critical pressure, the minimum pressure which is required to liquefy the gas. And in this case, it is 73 atmosphere pressure. And the critical volume is the volume of 1 mole of the gas at critical temperature and pressure. So at critical conditions of temperature and pressure, how much is the volume of 1 mole of the gas is going to be given by critical volume. Okay, so that is about the critical phenomena. Okay, critical temperature, critical pressure, and critical volume. Critical temperature is the temperature above which the gas cannot be converted to the liquid, no matter how much the pressure is. Critical pressure is going to be the pressure required for the conversion of the gas to a liquid, and critical volume, gas at a gas to liquid at the critical temperature, and critical volume is the volume of 1 mole of gas at critical temperature and pressure. Okay, now here, okay, so here you've been given a table in your textbooks. Okay, it consists of a substance with its critical temperature, pressure, and volume. Now observe the values for the critical temperatures. Okay. Now room temperature in, and all of these are in Kelvin. Okay. So room temperature in terms of Kelvin is going to be 273 Kelvin. Now notice gases like uh, maybe even carbon dioxide. Okay. Uh, Ammonia, and even water, all of these gases have a critical temperature above room temperature, which means they can be liquefied in the normal conditions by simply applying some amount of pressure. Okay. Whereas, and in fact, water, if you remember, if you notice, water does not even require a huge amount of pressure. Just by cooling, we manage to convert the vapors to a liquid and liquid to a solid. So these gases, which can easily, these are easily liquefied by just applying some amount of pressure. On the other hand, gases like oxygen or nitrogen, helium, hydrogen, all of these have the very less value compared to our room temperature, and they cannot be liquefied easily. And that is why they are called as permanent gases. They are referred to as permanent gases. So it was through all of these experiments that it was clear as to how important it is for us to decrease both the temperature, decrease the temperature just to liquefy the gases. Now, this is the last concept we'll be learning about, that is the continuity of state. What we're doing is we're going to see if there is some way we can try and, make sure we don't get this particular area, that is the gas plus liquid. So first of all, this particular shaded area which we get is by basically joining the various isotherms at different temperatures. So we would have had one isotherm at this distance, this length, then there'll be another one. So all of this gives us a maxima, that is X, which we learned about as the critical temperature and critical pressure, and the VC, that is critical volume. So, excuse me. So here in this area, within this area, carbon dioxide exists as both a liquid as well as a gas, right? Now, there are two states which are existing in this area. Now, let's assume we try and convert, we are taking the point A, okay, volume of gas is V1, okay, we're taking a certain amount of gas and we are heating it to a temperature, and this in turn ensures that the pressure has increased from here to here. So the pressure has increased from this particular point to this one. And we are arriving at point F. Okay. Now, from point F, gas is going to get compressed constantly from this to this. So we reach point G, where the gas gets converted from gas gets converted to a liquid with a huge increase in pressure. And then you have the decrease. This, when the gas is cooled down, it's going to get decreased. The pressure is going to decrease from G to H. Now, this case, when whatever I just said, A to F, F to G, and G to H, this actually shows, or G to D also, this actually shows us the continuity of state. Here, you do not have a condition where you have the presence of both a liquid as well as a gas. So we're not having that. Instead, we're just having, uh, we do not have a mixture of liquid and a gas forming in between, like in these cases, but we just have a liquid or a gas. We don't have both of them observed. So liquid is actually considered to be a very, very dense gas. Below the critical temperature, we can actually distinguish between a liquid and a below the critical temperature, pressure, and volume. We can distinguish the proper line between a liquid and a gas. However, when we reach the specific conditions of pressure, volume, and temperature, what will happen is the boundary between the liquid and the gas will start to disappear. Okay, and there is no particular way where we can actually distinguish between these two states. Uh, Not only that, below the critical temperature, it is liquefied easily. And this particular condition where the gas is below its critical temperature, it is referred to as vapor. And that's about continuity of state. So with that, we're done with the liquefaction of gases and the critical phenomena. We took the example of the isotherm of carbon dioxide. First of all, we talked about how it is important for us to decrease both the temperature and increase the pressure for us to liquefy gases. So we are decreasing temperature just to push the just to slow down the molecules. So if they're slow enough, then they'll come to a place where they can't overcome the attractive forces between the molecules. Then further, when the pressure is increased, they will tend to push the molecules closer to each other, and this in turn will help in the process of liquefaction. So a gas is liquefied by two ways, either by decreasing temperature or by increasing in the pressure, or it is done by both of them. So what we noticed was we started with the condition. We took first of all, the carbon dioxide isotherm. They were, or rather, the conditions for liquefaction was studied by Thomas Andrews in the year 1869. At 50 degrees, first of all, he took the carbon dioxide isotherm at various temperatures. So here at 50 degrees Celsius, he noticed that it was behaving like an ideal gas. And this is just a graph which is from the Boyle's law, that shows us the curve of for the ideal gas. So it's quite similar. So carbon dioxide behave like an ideal gas at 50 degrees Celsius. Next, at 30.98 degrees Celsius, it was noticed that there was a small line in between, and this in turn, as you remember, we talked about. So the 30.98 degrees Celsius, 73, and the volume VC is the critical points, temperature, pressure, and volume of carbon dioxide. This can be written as X. Okay, and in this condition, you have the small maxima, which is observed. Next, below 30.98, you have, below 30.98, first you have a gas which increase in pressure leads to the conversion from A to B. There's a decrease in volume. B to C, you have a mixture of both liquid and a gaseous phase. And adding in the pressure to the system will make sure that the liquid gas gets converted to the liquid, and at point C, condensation is complete. C then moves up to D, which means that even a small amount of decrease in volume requires a huge increase in the pressure. Okay, below 30.98, not only that, you also observe that there are other lines, so 13.1 degrees Celsius, but then this length is actually longer than compared to C, B. So the same pattern is observed in this case as well. Now, that's why we talked about the critical temperature, pressure, and volume. Critical temperature is the temperature above which a gas cannot be liquefied, no matter how much the pressure is. Critical pressure is the pressure which is added to the gas to liquefy it at critical temperature, and critical volume is going to be the volume of 1 mole of gas at conditions of critical temperature and pressure. Not only that, this area, the shaded area, represents the condition where carbon dioxide is in both a gaseous as well as a liquid state. A represents a point like A will represent carbon dioxide in gaseous phase, whereas points like D represents carbon dioxide in liquid phase. Basically, this area is going to be a liquid, this is a vapor and liquid, and this area is a gas. So comparing it to other substances, you have various, so for substances like carbon dioxide, water, all of these, the critical temperature is above room temperature, which is 293 Kelvin. So here, if you notice, 304.10, this is obviously higher than 293 Kelvin. So these gases can easily get liquefied by just adding pressure. However, on the other hand, in this case, you have gases like hydrogen, helium, nitrogen, and oxygen. These gases tend to liquefy below room temperature, and when some amount of pressure is applied, and so these gases are considered permanent gases. It was through all of these experiments that Andrews was able to figure out how important it is for us to decrease the temperature while liquefying gases. The last one is the continuity of state. So when we have a gas with a volume V1, it's heated to this particular temperature, that is 31.1. And then what happens is at 31.1, there's going to be an increase in pressure till point G, and then you have point H. So this shows a continuity in terms of state. You do not have the presence of a gaseous plus a liquid state happening like in these cases. That's not happening over here. And liquid is basically considered as a very dense gas. Not only that, at a critical temperature, normal conditions like below the critical temperature, you will be below the critical conditions of temperature, pressure, and volume. You'll be able to see the difference, or rather the boundary between a liquid and a gas. But when that point is reached, you won't be able to see the boundary between the two states. So with that, we're done with the liquefaction of gas as well as the critical temperature, critical conditions. I hope you understood it. If you have any doubts, do reach out by mail or like comment below. With that, we're done with this topic, and in the next video, we'll be continuing with the properties of liquids.